Good morning, afternoon, or evening, wherever in the world you're joining us from. And I'm Jarka Glassey. I'm the Vice President Executive of the European Federation of Chemical Engineering, EFCE. And I'm already in my second term as Vice President at the moment. I'm actually a biochemical engineer by training. I graduated from the Slovak Technical University in Bratislava, but I work in Newcastle University in UK, where actually I work a lot with artificial intelligence and machine learning methods, working with industry. And most recently, we've started looking into reduced order models in mixing and other processes, particularly in bioprocessing. So I'm really interested and very happy to be involved in the introduction of this webinar on reduced order modeling for mixing processes. And I'm so looking forward to the great program that we have. Let me just say a few words about the Spotlight Talk series. So this is now our 5th series of Spotlight Talks, which started in 2020 to help us keep together the community during the COVID pandemic. The success of the previous years convinced us to transform the Spotlight Talks into a regular feature of the EFCE program. And now we run one series in odd years and 2 in even years, like now in 2024. So this autumn, 13 of our working parties and sections are delivering over 2 weeks short sessions of 3 or 4 talks focused on specific topics by leading industrial and academic experts. And this series therefore enables attendees to sample various areas within chemical engineering research and practice and encourages them to cross-fertilize the ideas and interest across the wide range. And if you're interested in a complete program of the Spotlight Talks for this autumn series, you can always find it on the EFCE website. EFCE promotes scientific collaboration and supports the work of chemical engineers in 30 European countries, representing more than 100,000 chemical engineers in Europe. The working parties and sections cover all major specific aspects of chemical engineering and are in fact at the core of our organization, forming the scientific engine that delivers many of the EFCE activities. They provide an important forum for technical exchange and networking among chemical engineers in Europe. And I'm particularly happy that in this series of Spotlight Talks, we have the first contribution of the newly re-established section of sustainability, which ran its separate Spotlight Talk series yesterday and is running another one co-organized with the Working Party on Education next week. So before concluding, I would like to thank all the people who worked hard within the working parties, the sections, and EFCE itself for this initiative to happen and to be successful. And as always, the most heartfelt thanks go to EFCE's Martin Pu in Toulouse, who did most of the conceptual setting up and practical activities to make this webinar happen. So without further ado, I thank you for your attention and wish all the speakers and the attendees a fruitful and successful webinar. And I'll hand back the word over to the chair of the Working Party on Mixing, Mrs. Joelle Aubin. Apologies for mispronouncing the name. And she will take us through the webinar. Thank you, everybody.
Thank you so much, Jarka. Thanks for the great introduction. I think it's given everybody a nice overview of what these Spotlight Talks are about if you haven't attended any of these before. And I'd also really like to thank Martine Fuchs for having organized all of these. It's a big job that she has to do, twice a year or once a year, depending on the year. So, yes, my name is Joelle Aubin. I am the chair of the Working Party on Mixing. And I am a full-time researcher at the University of Toulouse in chemical engineering and particularly in mixing processes. And I am joined today by Claudio Fonte, who is the secretary of the Working Party on Mixing, who is from the University of Manchester. And we're really pleased to welcome you today to this webinar where we're going to be discussing reduced order modeling and how it can be used for understanding, developing, controlling mixing applications in the process industries. So if you're not familiar with ROM, it is a mathematical technique used to simplify complex systems by reducing the number of variables or equations needed to describe them. And this is typically done by identifying key features of the system that dominate the behavior of the system while ignoring less significant details. And in the end, it now enables much faster calculations with a minimal loss of accuracy. So in the case of mixing processes, which are typically very computationally expensive to simulate in full detail, particularly fully turbulent systems, reduced order modeling allows for faster and more efficient predictions, as it can capture just the key characteristics of the flow patterns and other related characteristics. And this then leads to cost savings, improved product quality, more efficient design of industrial mixing equipment and processes. So today we've got two presentations and that are going to give us different examples of using reduced order modeling for predicting process characteristics and performance in mixing applications. The first talk is on artificial intelligence-derived reduced order models and their applications in the formulation industries. And this is going to be given to us by Christopher Windows-Yule from the University of Birmingham. Christopher is an associate professor in chemical engineering, and he also works jointly with the Positron Imaging Centre, which is in the School of Physics and Astronomy at the University of Birmingham. And his research interests include the dynamics of particulate, fluid, and multiphase systems, as well as the development of novel experimental and numerical methodologies in order to explore these different multiphase systems. He also works closely with a number of industrial partners, particularly in the chemical, food, and pharmaceutical industries. Kit, I'm ready to hand over to you so we can listen to you, what you have to tell us about ROM and applications in the formulation industries. Thank you so much.
Thank you. Let me just share my screen.
Oh, hang on. Sorry, I forgot one important thing just before you start. To all of our participants, at the end of the presentation, or each presentation, you can ask questions, but you'll need to ask questions by the question and answer tab. Okay, so you can write it's not the chat, but there's a question and answer tab, and then either Claudio or myself will read out the questions to the speaker, and they will answer you. Okay, thank you. Off you go, Kit. Now.
Brilliant. Okay. So I'll start this talk by saying I'm coming at this perhaps from a slightly odd angle for this working group. So I will be talking about fluids, I will be talking about mixing. Sadly, I haven't got anything on fluid mixing specifically, so you'll have to use your imaginations a little bit, but the focus of what I'm talking about today is the tools rather than the content. So my hope is that you can envision some fluid mixing applications of these things. So Joelle's given us a beautiful introduction to what ROM actually is. So luckily, I don't have to do too much on my intro and motivation. I'm just going to give a brief overview of why we use ROM, especially why we use it in industry, and also why we might want to integrate AI with that. I'm then going to talk about a piece of software developed in my research group, which leverages symbolic regression and Gaussian processes to actually create reduced order models. I'll explain why we use those as well. And then I'm going to present a couple of case studies which are chosen more as a demonstrator of impact than anything else, showing sort of why these kind of simple models can be extremely useful, but also where their limitations are and when you might want to look beyond some of the simplified methods that I'm talking to you about today. And then, of course, summary and conclusions. So again, I don't have to labor this point. I don't think Joelle gave us a very good overview. Why do we use reduced order models? So computational efficiency, and in the world of Amazon Web Servers, that immediately leads to significant cost reduction. I ran a series of experiments, simulations recently on Amazon Web Servers. It cost £60,000 to optimize a single piece of process equipment, which was quite extraordinary. So if we can if we can reduce the cost associated with simulating items, like Joelle said, then that's very, very valuable. It also, crucially for industry, these reduced order models can be run very efficiently, which means that we can do real-time analysis, and through this real-time analysis, we can do process control, which makes things more efficient and less wasteful, and that's what we'll get in my case studies. They also allow for improved understanding. As human beings, we're not very good at interpreting enormous data sets or big simulations. Reducing it down into a simplified one-dimensional form can be extremely powerful. So why do we want to use AI for reduced order modeling? Well, AI is very good at capturing highly complex dynamics that can be extremely difficult to interpret for a human being, and certainly to create a theoretical framework around. They are extremely good at leveraging big data. And the thing about complex fluids and particles and, God forbid, multi-phase systems is that they are very complex. You need a lot of data sets to really fully understand them. And AI is very good at handling and interpreting these big data sets. And thirdly, I put possibly in brackets here because in the field there is some disagreement about whether AI models really can extrapolate outside their training data, whether they really can generalize this. I'd like to have that conversation with Jarka at some point, but possibly generalizability. So intuitively, one might think AI and ROM are a match made in heaven, but there are sort of, dependent on the type of AI you use. Certainly, if you use some of the more popular ones like transformers and artificial neural networks, not that they're particularly new, there are some certain contradictions, because in terms of improved understanding, certain forms of AI, things like neural nets, transformers, as much as we like to interrogate them, they are at their heart black boxes. They are difficult to interpret. So we stand to lose that kind of interpretability. In terms of computational efficiency, again, these models, though their inference costs are typically reasonable, and even then, if you use them at a large scale, they're still using a significant amount of computational energy, they are extremely expensive to train and will require a large amount of training data. So there is that trade-off. Dependent on how often you're going to use this reduced order model, by creating an enormous training data set, are you actually gaining a benefit? Luckily, though, they are extremely good for real-time analysis and process control. So to sort of hammer home my point about, the costs, the compute costs, and thus, in turn, the financial costs of training these models, what we find is as we go up and up and up and up in the complexity of the models that we're using, we are massively increasing the costs associated with training and developing these models. I want to draw your sort of attention. This is a log scale we're looking at here. And so this is, an annual 2.4 times more computational expenses each year passes as we develop these models. So personally, what I'm trying to try and convince you here is that we don't need necessarily to be up here with the types of AI we're using to produce our reduced order models. I would much rather be down this end using much simpler, slightly more old-fashioned, if you will, AI models that have much lower computational expense for the good of our pockets, but also for the good of the planet, because data storage and analysis are now using more, they're producing more greenhouse gases than the aviation industry these days, and I really am keen to contribute to that as little as possible. The final thing to talk about with AI, and I should specify that one of the hats I wear when I'm not an associate professor is I'm a independent scientific advisor for the Innovate UK Bridge AI scheme, which means I go around, I'm paid a day a week to go and talk to industry about adopting artificial intelligence. One of the big barriers we find, other than, people can't program very well and they don't know what they're doing, is that they don't necessarily trust it if they do. So transparency, interpretability, interrogability are all things that are ethically important. Another of my hats is I'm an ethics reviewer for the Alan Turing Institute, but they're also important to industry. Would we trust a true black box like an artificial neural network for the process control of a potentially dangerous system or to produce a potentially dangerous product. And the last time I canvassed a room full of industry specialists, the answer was a resounding no. So even this one, there is a question mark behind, because are they useful for process control if we don't trust them for process control? And that's a very important question in the field at the moment. The good thing is I'm talking specifically here about a subset, albeit currently the most popular subset of artificial intelligence. And there are techniques that can get around it. And this is the one that I'm going to talk to you about today. So this is rather a mouthful: multi-phase materials exploration via evolutionary equation discovery, or MED, as we shorten it to. If anybody's interested in the software, it's freely available on my research group GitHub. But what it does, it's a combination of two tools. It's got a Gaussian process engine, which means if you stick it to a simulation engine, it can automatically, so you can give it an initial set of points and it will automatically define the most appropriate next set of points to fill in the phase space and improve your model, and so on and so forth. But that's not what I'm going to focus on today, because this isn't a talk on DOE, this is a talk on ROM. What I'm going to talk to you about today is the other aspect of this software, which is its symbolic regression engine. And the reason I like symbolic regression is twofold. Number one, it is extremely, extremely cheap and easy to train. As you'll see in the next few slides, even if you've got a three-dimensional parameter space with a little more than 30 data sets, you can produce an extremely accurate equation. Compare that with trying to train a neural net, when you typically will be looking more around 10,000 data sets. It's extremely efficient, and considering how difficult it is to find 10,000 data sets in industry and how computationally expensive it is to create 10,000 data sets simulationally, again, we're talking 30, 40, 50,000 pounds on Amazon Web Services here. Being able to do it with a small number of data sets is extremely powerful. The other reason I like symbolic regression is it doesn't give you a black box. It gives you a closed form mathematical expression. So it is the control mechanism you get out of it is entirely interpretable. And to me, that's extremely powerful. So yes, as I say, it's efficient, it requires relatively few data sets. And of course, what it spits out is not a model, it's an equation. So you can run the darn thing with basically zero inference costs. You can run it with pen and paper if you really don't want to have any energy costs at all. It produces closed form mathematical equations, so it's eminently interpretable. And the really exciting thing about it, and again, what I will happily get into an argument with real ML specialists at the end of this talk about, is in the right circumstances, I'm very confident that it's generalizable, because what it can do is it can actually discover the real physics at the heart of the system. Now, of course, there has to be some physics at the heart of the system for it to do that, but as I will show you in a few slides' time, it is exceedingly good at doing so. So how does this symbolic regression, this what I like to call evolutionary equation discovery, actually work? So it starts off, so effectively it works. The easiest way to think of it is, think of it like linear regression or non-linear regression, but instead of giving it a fixed functional form and letting it choose the coefficients to this form, what you're doing instead is letting it choose the coefficients and the form. And that's the crucial thing, because it allows it to find extremely complex, confounded, convoluted variables and combinations thereof. So it starts with a pool of functions, and you can choose which operators you allow it to use. So plus, minus, times, cos, sine, exponents, etc., etc. And what it does is it takes this pool and it tries, just like a normal evolutionary algorithm, it tries random combinations of these different parts of an equation. It then tests the candidate equation. So here is the curve that we're trying to fit, and here is the two initial guesses via symbolic regression engine. And based on the success of those fits, it eliminates equations that are poorly fitting, and it then goes on to the next step of its evolution. It takes the ones that fit well, and it evolves them into the next form. It then repeats this process. It tries fitting the new ones, and over enough generations, it eventually finds an equation that near perfectly, or I say near perfectly, fits the true form, or at least fits it as well as it seems to be possible to fit it. And it does so again by creating piece by piece through an evolutionary process these algorithms. Now, obviously, that is an obscene simplification of what it actually does. It doesn't just produce two equations every epoch, it produces hundreds. It doesn't just do 2 epochs, it does thousands. But the point is, it's this simple evolutionary process, tweaking the ones that work, eliminating the ones that don't, until it reaches a sensible answer. So as I say, it's not really having 2 guesses, it's having dozens of guesses, and it's doing so over thousands of individual generations. And what we end up with at the end of all of this is something that looks like this. We end up with this kind of Pareto front of possible optimal solutions. And I say possible optimal solutions because we don't just get one optimal solution, because obviously there's a balance to be had. And I'll explain what I mean by that. So on this plot, what we're looking at is each point on this represents a possible guess at an equation describing whatever it is that we want to model. And it's plotted on axes of residual or loss against complexity. So the residual is effectively the error. How good is the guess? What's the difference between the predicted value from our model and the ground truth data from our experiment or our simulation? But on the other axis, you have the complexity. How concise is the equation? The higher the complexity, the more terms your equation has, the more complex, possibly unnecessarily complex it becomes. And this is what I mean by there being no true optimum, because the best fit is not necessarily the best equation. So on the one hand, you have these equations up here, which are beautifully simple, but massively inaccurate. We have a very high loss, a very high residual. At the other end, though, we have phenomenally low residuals. This fits it with almost 0 error, but we've got 60, 70, 80 terms. We are overfitting this data quite considerably. You also see really interesting features like this, which is where the equation discovery has had a breakthrough. So it can massively reduce the residual without making the equation much more complex. But the points that we are most interested in are the ones like this, where we have a very low residual, so our equation fits extremely well. We also have relatively low complexity, so it's not sort of a horrible, monstrous overfit as we are prone to get with AI. So this all sounds very neat, very nice, very well, but does it actually work? That's the crucial question. So the first thing we did when we developed this software was we wanted to actually prove that it can find the true physics, not just a good fit, but it can find the true physics in a set of data. And we wanted to make it difficult. So we started by doing some DNS simulations of creeping flow around a spherical particle. And just to make MED's life harder, we only ran 32 simulations, because as I say, one of the reasons I want to do this is to make something that's sustainable, that's low computational cost. So we start with this small training data set, and we vary fluid viscosity, particle radius, and flow velocity. We do so with a Sobol distribution, so it's relatively easy to, it's filling the phase space pretty well. And then we measure the output, so those are our inputs, the output is the force acting on our particle. And we feed these 32 data sets to our symbolic regression engine, and we get an output that looks a little bit something like this. So our first generation, as I say, it's an evolutionary algorithm, so all it's doing is throwing together things in completely random combinations. So we end up with stuff that's simple, but clearly completely bonkers. And then we end up with stuff that's complex, but also completely bonkers. So we're having sort of a logarithm of a function, and it's completely unphysical because we can have a non-zero force with zero flow. So it's not doing a very good job so far. However, if we wait and look at one of our later iterations, we start to see something that, if you squint hard enough, starts to make a bit of sense. So let's take this specific equation here. So obviously it gives it a phenomenally ugly form, but if we take our R up to the top, simplify the numbers down, what we get is something like this, which is approximately 6 pi R mu u, which is, to within a 2% deviation, we've just rediscovered Stokes's law. But completely by itself, we literally just fed it 32 data sets, said go, and it rediscovers Stokes' law for us, which I think is fantastic. The really interesting thing is actually the equation that Med has derived fits the data better than Stokes' law. Okay, because obviously maybe there's some errors on the data. Maybe Stokes was simplifying his 6 down a bit, but the point is, it more or less discovers it, and if it's the error on it is actually making it fit the data slightly better. It also got here relatively rapidly. We were going to let this run for 320,000 iterations. It derived Stokes' law in 122. So tremendously computationally efficient. We also did something similar with the Darcy-Weisbach equation. So we did 32 DNS simulations of laminar flow through a pipe varying viscosity, fluid velocity, pipe radius. I won't give you the same chat, but the point is it discovered an equation, we rearranged the equation, and you get something that's plus or minus 5% the Darcy-Weisbach equation, which is pretty darn neat. So I'm now confident that this piece of software works. It's rediscovering the equations we'd expect to be rediscovered with an error that is only causing it to fit the data better rather than fit the data worse. This point, I always like to set a challenge. I with a piece of software like this, I'm always keen to see how far we can push it before we break it. So if anybody does have any sort of classical chemical engineering or even classical physics equations that you'd like to test us on, I'm very open to suggestions in the comments at the end. So that's symbolic regression in a nutshell. That's why I like it. That's proof that it actually can do something. It can rediscover old equations written by dead scientists from 100 years ago. Can we do something useful with it? Because obviously that's the whole point of this. So the first case study I'm going to talk you through, this is some work we did with AstraZeneca looking at pharmaceutical blending and continuous direct compression. As I say, it's a mixing problem, but it is a powder mixing problem. So for those who aren't familiar with the pharmaceutical industry, continuous direct compression is a beautifully simple process. You feed all the different components of your tablet, so your active pharmaceutical ingredient or API, then one or more excipients and lubricants and bulking agents, whatever else you want to do to make it into a tablet. You feed these all in together, you pass them through a blender, and then you compress them into a tablet. And this is one of the big shifts. The continuous part of continuous direct compression is a big shift. Indeed, it's one of the most fundamental shifts that's been going on in the pharmaceutical industry over the past sort of couple of decades. And I'm working on several projects with AstraZeneca looking at various forms of continuous manufacturing because it offers some significant advantages. It's higher throughput, it minimizes waste, it reduces the innate error of batch manufacturing because there's a lot of human interaction with it, and it's extremely easy to scale. The problems, however, it's a much more complex process, but crucially, because it's a new process, we can't benefit from the hundreds of years, or at least decades, of experience that pharmaceutical companies have working with batch manufacturing. So herein is the problem. You don't have the experience, you don't have the predictive capabilities. Because the crucial thing, particularly with the mixing aspect, is you have to think about mixing on both the macro level. So you have to make sure that you can smooth out these perturbations, these imperfections in the way that the material's fed into the system. But you also have to have the micro mixing correct. So you actually have to have it correct on the particle scale, because obviously these are pharmaceutical tablets. If you have a tablet that has too little API in it, it's not going to cure the disease that it's meant to cure. If you have the risk of too much API in the tablet, you might end up straight up killing somebody. So getting both the macro mixing and the micro mixing right is incredibly, incredibly important. So to distill all this down into a problem statement, we lack understanding about continuous blending, and this is holding back this transition to continuous processing, which can save huge amounts of time, waste, money, energy. But we don't have, as it stands, predictive models allowing us to simply measure, because I suppose this is the point. This is the kind of point that I haven't really emphasized well enough perhaps yet. If this was a batch process, I can measure my powder, and I can predict from that measurement how it's going to behave in the feeder, and then I can measure what I get out of the feeder. I can characterize that again, and then I can put it back into the mixer and I can characterize it again, etc., etc. With the continuous direct compression, I have to be able to predict the mixing quality before the feeding stage. So it's a much more complex prediction. So what we want to do is develop a simple, interpretable model where we can do a couple of simple measurements of a powder, we can stick it into our continuous direct compression process, and we can tell whether we're going to get the right dose in our tablet at the end of this process. So what we did was we took in this case, it was 4 distinct variables. So we're looking at the feed rate. So this is a bladed mixer. So we've got, I forget again, for those who aren't familiar with all of these things, this is a bladed mixer. You feed the material in here. The blade's transported up to the top, out of the bottom, and you weigh what you get. So we're varying the feed rate, the RPM, the mixing blade, and crucially the materials. And we're measuring the residence mass within the feeder. The reason we vary the residence mass is an extremely good proxy for mixing quality. There's been some extremely nice work done by Palmer and colleagues that's shown effectively that the mixing quality of a powder is directly proportional to the strain on the powder. So effectively the work done on it during the feeder, which is a function of the residence mass, the residence time within the system, and the blade rotation rate. So if we can predict this residence mass, we can predict the quality of the mixing. It's a really nice proxy measurement. And this is knocking on the door of big data, because as I said, notionally we've only got 4 variables, but in actual fact we've got nearer 10, indeed more than 10, because the material properties, we've got basic flowability energy, which we've used at FD4 rheometer, we've got bulk density, we've got the wall friction angle, we've got the D10, the D50, the D90, we've got the conditioned bulk density. Again, it doesn't matter for the moment if you're unfamiliar with these measurements, but the point is we have a significant data set here that we want to try and condense down into a simple, meaningful set of measurements. And that, luckily, is one of the things that symbolic regression is very good at doing. So this is the final equation you'll get out of it. And what you'll notice here is that you don't have a dozen different variables. One of the real strengths of symbolic regression, you could also actually use it in a way for sensitivity analysis, because it's extremely good at discarding the variables that don't have much of an impact and only including those that are particularly relevant. So it's kept the feed rate of the material into the system, which makes sense, the number of blades on the mixer, so this is telling us something about how we can optimize the geometry of our system, the rotation rate, the wall friction angle, and the D10, so a measure of how many fine particles we get in the system. All the other stuff, it's thrown away, and it's given us a pretty decent prediction. So an R squared greater than 0.8, the predicted values that this model is giving us are reasonably close to the experimental values. And this has some real-world benefits. This is why I like to use this example. Perhaps it's not the most ROM-tastic example I could have given you, but it has real-world impacts because their internal analysis has shown that this process should save them on average £176,000 per design of experiments performed in their R&D department. This isn't an annual saving, this is per design of experiments, and 21 tons of carbon dioxide. We did some similar work. I'm not going to labour the point on this, but the point is this is more of a process control example. We did some similar work with GlaxoSmithKline, this time looking at a wet granulation process, which is another way of producing tablets in the pharmaceutical industry. And what we did, we stuck a force sensor into their granulation process. And the question was, from measuring the forces acting on this sensor, the torque acting at the base of the system, and of course the compression pressure with which we create the tablets, can we predict the outcome of this process? And the answer was a resounding yes. And beautifully, again, we fed it about 8 different parameters. It threw everything away except the integrated force during the water addition phase of the granulation and the compression pressure, the load that we applied to the tablet at the end. Threw everything else away and gave us really rather a good correlation, predictive correlation for this output. Again, I'm not going to sort of labour this point. I'm coming to the end of my talk time. If you're interested in it, you can certainly ask me more questions. But the point I wanted to make out of these 2 examples was it can have real-world impact. GlaxoSmithKline have now funded another project with us with the aim of actually rolling out this technology and this set of predictive equations across their pilot-scale plants first, and then eventually their commercial lines. And it could work on various different processes. The final note to make here, though, of course, is that there is always a trade-off, okay, between accuracy and ease of interpretation. So we've been talking predominantly about symbolic regression, but there are various other ways of analyzing this kind of data. So for the same data set, we also applied an artificial neural. So this is for the AstraZeneca data set. We also applied an artificial neural network, and we applied random forest regression. And what this showed us very clearly is, although these more interpretable methods give us reasonable predictive capability, the neural net did certainly outperform them in terms of its ability, purely predictive capability. However, in terms of interpretability, something like a random forest regressor actually gives us a decision tree, which is interpretable, even to those who aren't particularly comfortable with the mathematics that symbolic regression might come up with. This is the kind of thing you could just pin up on the wall in your factory, and the operators can simply look at that and say, right, okay, this is the path I need to go down if I want to get this particular outcome. In the middle somewhere there, you have symbolic regression, which gives you these very interpretable sets of equations and also gives slightly better accuracy. And then at the top there, you have your black box, which gives you very good results, but ultimately it is a black box. So it's a case, in my opinion, of horses for courses. Do you want something that you can fully interpret that gives you a very reasonable estimate, or do you want a better estimate for something that you don't understand necessarily the inner workings of? And dependent on what you're trying to do, you can make either one of those choices. So to summarize, artificial intelligence and reduced order modeling can give us valuable new insights into a diverse set of processes. I've shown you 2, one mixing, one not, but a similar approach can be applied to any sort of experiment simulation that you can think of. Despite some limitations, I'm not promising the most accurate piece of AI in the world, but it gives us very interpretable, extremely efficient ways of calculating, producing reduced order models, even from the kind of sparse data sets that we really wouldn't want to throw some more complex techniques at. And we've also demonstrated that it can not only correctly, but also extremely quickly rederive some fundamental chemical engineering equations. And that's, to me, is an important thing, because what it's showing us, it's not just giving us an ugly fit. It's actually finding the real physics that describes these systems, assuming that such physics is there, which makes it really quite a powerful tool in terms of being able to interpret and extrapolate beyond necessarily the data set it was trained on. So that's all from me. Any questions?
Right. Thank you so much, Kit. Very, very interesting. And I think it was really clear. I really enjoyed the overview and you placing ROM and the different types of models that we can have, and the level of interpretability versus precision, and it is, I think, it's weighing things up and compromising, and I think that's just the life of a chemical engineer, is compromise. But you have to compromise depending on what you want as an outcome and what you want as information. So
if we want the industry, of course, yes.
Of course. So we have a question. Claudio, do you want to read that out?
Yeah, I can read that out. It was indeed a great talk, Christopher. It was really nice. So the first question is from Alain Ninet. So he says, thank you for this very interesting presentation. I have several ideas to play with the MED or M2E3D. Concerning the MED software, why search for expressions based on dimensional quantities rather than dimensionless numbers? Oh, sorry. For example, for creeping flow around the sphere, why not look for the drag coefficient as a function of the Reynolds number, for example? This would avoid generating correlations with dimensional coefficients that are difficult to interpret.
So the first answer to that is yes, absolutely. There's no reason you can't do that, but effectively, this wasn't. You got to remember, this isn't us really using it as we would use it in real life. So one of the powerful things you can do about it, you can use these dimensional groupings. If you know some of the physics of the system, you can actually feed it entire chunks of equations or sub-equations that you would like it to use. But the point of these exercises was to give it a hard time. We didn't want to give it any of our prior knowledge and see what it could work out on its own. So in real life, absolutely, if you've got some understanding of the systems, if you know what the governing sort of sub-equations are, if you know what dimensionless numbers it should work with it, you can feed it those and let it use them. But those particular examples were just us trying to really see what it can do if we don't help it, if that makes sense. Darn good question.
But if I can follow up just very, very quickly, even if you don't know what is the expression that you are looking for, right, and you don't know what are the non-dimensional numbers that govern the flow, can't you just use normalized variables like velocities that will be normalized by characteristic velocity or something like that, so that you ensure that the expressions that you get at the end are non-dimensional or dimensionally consistent?
Yeah, absolutely. Of course, you could absolutely do that. Again, it depends on what your ultimate goals are. So, for instance, with working with the stuff from AstraZeneca, we just wanted to use the things that were directly measurable by them. Mm-hmm. But if you were interested in making something a bit more beautiful, then absolutely, there's no reason not to do that. It's one of the big advantage of it is it's an extremely flexible framework. You can put in whatever you want as the input variables, and you can handle them however you want, and the same for the responses.
That's great. So there are some more questions. Joelle, stop me if we get out of time. But so I have a question from Syed Hosseini from Toulouse. He says, thank you very much for the talk. It was really interesting. I was wondering if I could ask, is the process of discovering equations in this method based on stochastic or probabilistic techniques? If so, could you elaborate on how randomness or probability is used to evolve towards simple and more accurate equations, like regression equations?
Yes, absolutely. So at its heart, that part of it is simply an evolutionary algorithm or a variant thereof. So it works like natural selection. So the first generation is completely random and it's completely random. And what it will do is it assigns a score to each of them. So it measures two things. It measures the complexity. So how many individual parts does the equation have? I won't say terms because it's not terms, it's individual. A number, an operator, everything else counts as a degree of complexity. And then on the other hand, you have the loss. So you have a measure of the inverse of accuracy. And what it does is then puts those two things together to give a score. So overall, how accurate is it per unit of complexity, if you see what I mean? And then what it will do, based on that score, the ones that have a very low score, it will kill them off. And then based on the ones that have a high score, it will then take those equations forward and it will apply some form of mutation to them. So it will either add extra terms on, tweak existing terms, that kind of thing. Now, one of the really nice things about that is because the score is a slightly subjective, it's a slightly subjective thing. What's a good score? There is no answer. That's why we have a Pareto front. But what you can do is you can choose to penalize certain things more harshly than others. So, for instance, one thing that's very common to do is nested exponentials. You can penalize nested exponentials extremely harshly because very few things in life have an exponential to an exponential to an exponential. So you can adjust the score to be more or less suitable. Crucially, though, at every stage, it doesn't give you one answer. This is another reason I like evolutionary algorithms. It doesn't give you one answer. It gives you a family of answers that you can then plot on that Pareto front, and you can choose the one that, based on your intuition and your knowledge of the problem, gives you the best combination of loss on complexity. So I hope that helps a bit.
Great. Shall we still have more time for some questions?
Yes, you can still go. We've still got 5 minutes.
So there's a question from Christian Nerger. He says, super interesting presentation. And the question is, what kind of training needs the AI used? So how do you do the training, basically?
So the training of the person operating it, or the training of the AI model? To be fair, I can answer both.
I think it would be the AI model. I think.
Yeah.
So sorry, can you read me the question once more?
So the question is, what kind of training needs the AI that was used? How do you do the training?
Okay, so what I've just described is the training, if you will. So you give it those data sets, and it will try and create a model to fit them. It will give you the loss of the fit of the model of the 100 or so models it creates, and then based on that input, it will adjust and adapt the next generation. So it goes generation by generation by generation. It's using Darwinian evolution to evolve a functional form that better fits the training data set that you've given it, if that makes sense.
Your last question, that's okay. So there's
2 more to go.
We still have time. So it is Tiziana Morella. So I have a question regarding symbolic regression, especially the number of data sets necessary to obtain a good result. It is necessary to have a large number of data, or it works well also on a small data scenario.
So exactly that. This is one of the main reasons that I used it. So the 2 examples that I gave you for rederiving Stokes' law and rederiving the Darcy-Weisbach, that was 32 data sets. It's a phenomenally small amount of data by machine learning standards. And that's what's really, really powerful about it. That's why I like it so much, that the operations it uses are incredibly computationally efficient. The data sets it uses are incredibly easy to obtain, which means and it's fairly noise tolerant and fault tolerant. And all this beneficial stuff as well, which means if you're trying to work with industry who are not good at just here's 10,000 data sets we've rolled off the factory line to train your model. They don't like doing that. So having something where you can say, look, can you do 32 runs of this high shear mixer for us? They'll say yes. And then if you've got a 3-dimensional parameter space, you can build a model around that, in my experience.
But if I can add to that, the data that you used to fit those 2 equations, they are quite nicely obtained from CFD, right? They are very smooth sets of CFD data, quite nicely behaved. Maybe industrial data would be a little bit more noisy and difficult to...
Categorically, yes, absolutely. But again, it's a fitting problem. So that noise will cause some issues, but it shouldn't cause tremendous issues. It's reasonably good at ignoring significant outliers, for example. And of course, the first 2 examples were CFD. The second 2 examples were real industrial data obtained on site at AstraZeneca and GlaxoSmithKline, and you still get these rather reasonably accurate models. And of course, with industry, reasonably accurate is kind of what you're going for.
Maybe a final question, Joelle?
Yeah.
Yeah. So from you, Jan. So she says, or he says, thank you for the really interesting talk. I would like to ask about the following. When applying symbolic regression to very complex realistic processes, such as mixing processes, does it need more input parameters to be considered? How to determine how many training data sets are required for symbolic regression applied to such processes?
Yeah. So this is unfortunately one of those questions where it's a little bit how long's a piece of string. There isn't a firm answer to that. What we found heuristically, if you've got a three-dimensional data set, 32 data points will fill it. If you go to 4 dimensions, then with about 50, it still seems to work. But it is very much, one of those. That's why the bit of the software I didn't talk about today was the Gaussian process engine. And that's why we included that in the package, because what you can do, let's say you've got a complex process. You start off with taking, say, 10 data points, okay? And what it will do is it will take those 10 data points and it will fit a model to that, and it will assess the error and all the rest of it. And then it will recommend the next 10 data points for you to take. Now, if you're doing this with CFD, you can have that as simulation in the loop. So it will take 10 data points, fit a model, assess the quality of that model, predict the most useful next 10 data points to take, launch and run and analyze those simulations, fit a new model, and it will keep going through this process until it's given you the right number of data sets. So you don't have to know a priori how many data sets, because it will help you do your DOE for you.
Okay. Right. Thank you, Chris, Kit. It was a fantastic talk. There's one more question. Can I please ask you to type the answer in the chat just to the person? It's Alper Koinichu. Okay, if you don't mind answering that, and so that we can move on to the next talk. Thank you.
Absolutely. Thank you very much. Take care.
Thank you.
Okay, so we're ready for our second talk now, and this is going to be on the reconstruction of large-scale structures and stirred tanks using reduced order models and using limited sensor data. And it's going to be given to us by George Papadakis from Imperial College in London. Now, George is professor in the Department of Aeronautics in the Faculty of Engineering. So it's nice to have someone outside of chemical engineering, but also knows about chemical engineering processes and other things, and gives us a view from a different aspect, a view from a different aspect. Now, George, before he was working at Imperial College, he was at the Department of Mechanical Engineering at King's College London. And he is interested in fundamental analysis and control of transitional or turbulent flows in various types of systems, aerodynamics, of course, but also chaos and mixing processes. And to do this, he uses numerical methodologies, so no experiments from what I understand, and he uses direct numerical simulations and large eddy simulations and various in-house algorithms. So, George, welcome, and we're ready to listen to you.
Thank you very much, Joelle. Thank you very much. Let me share my screen. Can you see my screen? Good. All right. Let me also put the pointer. Right. Okay. Thank you. Thank you very much as well for this introduction. So I'm going to talk about the reconstruction of large-scale structures in stirred vessels using ROMs and limited sensor data. So you indeed, as well said correctly, I will look at this problem from a slightly different perspective, and hopefully will be useful for the community of mixing. So I want to acknowledge the work that was done. This is the PhD work of Kirill Mikhailov, and I would like to acknowledge also the funding from the Center of Doctoral Training Center from the Fluid Dynamics Across Scales. So let me give you some context and the motivation behind this work. So the idea is the following, that within stirred vessels, we have numerous studies, both experimental and computational, that shows that within very complex three-dimensional rotating flow fields, turbulent flow fields inside stirred vessels, we have large-scale structures that are forming in the vicinity of the impellers and the whole tank that can take different forms. They can be trailing vortices, they can be macro instabilities, etc. So these are very large structures. These are large three-dimensional structures that are rotating inside the stirred vessel. And these are crucial for determining the mixing performance and the product quality. Okay. So if we want to improve the mixing performance and if we want to improve the product quality, we need to know the shape of these structures, the spatial three-dimensional shape of these structures, and also know the strength of these structures, how much energy they have, and where is this energy concentrated. So there are various methods. So we need to know this information in order to be able to exploit it in order to enhance performance and product quality. Now, there are various decomposition methods, in particular orthogonal decomposition, that has been applied to characterize and extract these structures. So these methods have been applied experimentally on 2D planes, numerically also in 2D planes, and there is also some work on 3 dimensions. And this is how so far we have been able to characterize these structures. So as I said, both experimentally and numerically, these structures have been observed. Now, if you look at the synergy between experiments and computations, you will see that up to now, what we are doing in order really to bring the two together is really to use experiments to validate our numerical simulations. Okay, so we are not doing, in the vast majority of cases, experiments are used, well, of course, to characterize experimentally the flow, but in terms of synergies with simulations, we use the experiments to compare and validate the simulations against. Now, the question is this: is there, within the context that I mentioned earlier, the concept of optimization, of mixing optimization, is there anything better than we can do? Is there something that we can do to bring together the simulations and the experiments in a way that will allow us to characterize the spatial and temporal location of these structures? And my purpose in this talk is to tell you that, yes, this is possible. And we can actually indeed reconstruct large-scale structures from sparse experimental data. And I have to add here, in real time. Okay, so we get the sparse experimental data, and in real time, we can have the spatiotemporal features of our three-dimensional structures, so we know exactly where they are and what velocity they carry, what energy they carry, so where they are spatially and what strength they have. Now, how do we achieve this? Now, the idea here is to bring together 3 different strands. So, of course, reduced order modeling, because it reduces the dimensionality of the problem. Then we have a second strand, which we call system identification, and I will explain later what it is. And a third strand, which is called linear optimal estimation theory. Okay, so this is a very well-developed theory for linear problems. If we want to go to nonlinear problems, then we have to use machine learning. But in my talk, I will focus on linear optimal estimation, because as you will see, this gives me the additional advantage of being interpretable. Okay, so the matrices that I'm going to get are interpretable. So starting from the equations, I can get exactly what these matrices mean. So it is interpretable. So I know how these matrices that I'm going to get depend on originate in the original equations. So then once we can do that, we can apply the algorithm to do optimization at design and new operating conditions and off design conditions. And we can use the reconstructed flows to quickly perform simulations to determine scalar mixing, find optimal injector locations, and so on and so forth. So let's see how. So I will say a few more things later on towards the end of my talk. Once you have seen how it all works, what we can also do, and what new doors this idea opens. So let's see. So we are doing simulations on a stirred vessel, a cylindrical stirred vessel. You can see here the dimensions. The vessel is stirred by a Ruston impeller. In particular, we are looking at unbaffled stir tanks. It's easier to perform the DNS simulations in an unbaffled stir tank, but all the methodology can be applied to baffled stir tanks as well. We are, since the stir tank is unbaffled, we are solving the equations in a rotating reference frame. So what you will see later on in terms of power spectra and the peaks of power spectra, the frequencies that we get for the peaks are referring to a rotating reference frame. So if we want to convert back to a laboratory frame, then we have to do a simple transformation. We are using a DNS in-house code. I'm going to show you results for a relatively low Reynolds number. In the first case, so we are using 600. The flow is transitional. Later on in the talk, I'm going to show you results for a fully turbulent flow of Reynolds number 30,000. And you can see here some results with respect to the time steps, rotations that we have collected, etc. Right, okay, so let's see. Very briefly, how we got the POD modes from this case. So we used the data from 210 rotations. We placed the data in a snapshot matrix. We perform singular value decomposition of this matrix, and that will give us two things. It will give us the spatial modes phi I and their time coefficients, which I call AI. Okay, so then my data, the velocities, the velocity fluctuations at every point and at every time instant are linearly transformed into this product where phi is the matrix of my POD modes and A are my time coefficients. So we have done that for this case, for Reynolds number 600, and you can see here the spectra. So on the vertical axis, we have the energy of the mode, and horizontal axis, the mode number. And you can see we have two modes that are dominant, so they have equal energy. So each of these modes have 14% of the fluctuating kinetic energy, and then we have additional modes 3 and 4 with about 5% of this energy, and then following that we have additional modes that contain a smaller amount of energy. Now if you look here, I have this green line that has a slope of minus 11.9 that matches very well the slope of the mode numbers of 100 and onwards, and that minus 11.9 can be derived from the minus 5/3 law of Kolmogorov for homogeneous isotopic turbulence. So at very high Reynolds numbers, we have modes, we capture modes that are encountered in homogeneous turbulence. And in the right-hand side, I show you the total energy with respect to the mode number. So you see that mode number 0 here contains most of the energy, so it's 86%. So mode 0 is the time average flow, okay? And I need about 100 modes to get 95% of the total energy. Let me show, so as I said, the modes 1 and 2 have equal energy, and it turns out that they are paired. So what does paired mean? So before I get into that, I'll show you the mode 1 and mode 2 on the top of this slide. So this is a cross-section, so we have computed the three-dimensional shape of these modes. So on the top row, you have the mode 1, and on the right, you have the mode 2. And you can see that these modes are essentially, mode 2 is shifted on the theta direction, on the azimuthal direction with respect to mode 1. And also, if we look at them, time variation, the time signals, there is also a shift with respect to time. So putting together modes 1 and 2 gives a rotating structure, as we will see later on. If you look at modes 3 and 4, then you can see again that they are shifted with respect to the azimuthal direction, and then They have also spatial structures which are almost half, so in terms of spatial scales, that are almost half compared to the modes 1 and 2. So as we increase the mode order, we get smaller and smaller structures, and eventually, as I said, we get to a situation where we have structures that approach homogeneous isotropic turbulence. In terms of the vertical plane, so here we have again modes 1, 2, 3, and 4, where we can see the shape of the mode in a vertical plane, which is bisecting the blades. Okay, so this is 6 blades, so we have it, we take a plane bisecting the blades, and what you can see is the footprint of mode 1 and mode 2 in these cross sections. And what you can see is that these modes are produced within the impeller, and they are radially propagating outwards. They hit on the vertical wall, and then they are deflected upward and downwards, and they almost occupy most of the volume of the stirred vessel. Okay, similar thing is happening to modes 3 and 4. Now, if we look at the spectra of the POD coefficients, here are the spectra, and you can see that mode 1 has a very sharp peak at frequency 1.fn. Fn is the impeller rotational frequency, and I remind you that this is frequency we obtained on a rotating reference frame. So mode 2 has exactly the same frequency peak at the same frequency and the same strength because the modes are paired. Now mode 3 has a frequency at 3 Fn, so it is the harmonic of 1.5, and as I increase the mode number, then I get more and more frequencies, more and more frequency content across the whole range of frequencies that I'm looking at, okay, from 0 to 5 Fn. So here for mode 61, I get up until 2.5. Then if I increase further the mode number, I get to 252. So as I increase mode number, I get smaller and smaller structures, and these smaller and smaller structures fill up the frequency spectrum, and as I said, eventually I get to something which very closely resembles homogeneous isotropic turbulence. Now, okay, let me show you now how the flow looks like. So here you will see I have put together modes 1 and 2, and I have run a simulation to show what structures do they represent. Okay, so this is the structures that are represented, and you can see that these structures are rotating around my impeller. The impeller rotates in the counterclockwise direction, while these structures are rotating in the clockwise direction. So they are rotating in a sense which is opposite to the rotation of the impeller, and they represent precessing macro instabilities. So this is okay. So now let's see how we can extract these structures, the location and the strength of these structures, with aid of measurements. Okay, because we can see these, we can have from the DNS simulation the shape of these structures, but we don't know their instantaneous location in the vessel as the impeller is rotating. So how can we reconstruct in real time their location and strength based on instantaneous experimental data? So I start with my governing equation. So at the top here, let me put the pointer. So at the top here, I have the Navier-Stokes equations written on a rotating reference frame. I use standard Reynolds decomposition. I compute the runs. I get the runs equation. I subtract these two sets, and I get a set of equations for the fluctuations around the time average, right? So what I have done here is that I have written the full set, but on the left-hand side, I have kept the terms that are linear with respect to the fluctuations. And on the right-hand side, I have kept the nonlinear terms of the fluctuation. So you can see here, u prime squared, while on the left, you have only u prime. Okay, so what then I do? So I have on the left the linear terms, on the right the nonlinear terms. So what I do then is I take my decomposition, my POD decomposition that you can see here, and I substitute it to the equation for the fluctuations. Okay, and then I know the theory. I can apply Galerkin projection take into account that my POD basis is orthogonal and divergence free, and I can eventually get a system of equations that is giving me the temporal evolution of these POD coefficients. All right. So this is the form of the system in symbolic. This is what the system looks like in symbolic form. So I have a term which is linear with respect to A, and that term originates from the previous term that I showed you here with the greenish background. And then the non-linear terms, when we project them to phi, will give me this F here. Okay? So this is my equation of propagation of the POD mode. Of course, now I assume that I have a set of measurements which are taken at P points, and I can very easily write my measurements in terms in terms of the coefficients A plus GT, which is the process noise, right? So very easy. I have the matrix. So phi are the POD coefficient, the POD modes at the point of measurement. So that very easily I can create this matrix S, and G is the measurement noise. So then what do I have? I have a system which is has a linear term and non-linear term, and a set of measurements that are related linearly to the POD coefficients of my ROM. Now, I can consider these non-linear terms as a noise term of my linear system. So I can think about this linear system as containing these linear terms plus a set of terms which I can consider as non-linear forcing. And I can consider them as noise to the linear terms. So then what I know is the following, that if I consider it like this, then I can produce an estimation of these A from actual measurements using the Kalman linear estimation theory. Okay, and I know from the theory that if I have my actual measurements, then I get an estimated coefficients, and eventually if I do the algebra, I have this system here on the right, right? So S is are my measurements, and then AE are my estimated POD coefficients. Now, you can see that, so why do I need this S? Well, I need this S because I don't know this nonlinear term, okay? I don't know the nonlinear term, but I have actual measurements, okay? So then the theory is telling me that I can obtain a form of the estimated coefficients, which has this functional representation. So now I know that this matrix exists, but is not known. I know that this matrix exists, but it is not known. If I want to get them, I need to perform the Galecki projection. But that's not the idea. What I want to do is to extract these matrices directly from data. This is what I'm doing. So how does this work? So the idea is the following. I run my simulations, let's say for 80 revolutions, and I use the 40 revolutions from 0 to 40 as the training data set, and the revolutions from 40 to 80 as the validation data. So I split it in half. So in the training data set, I have the measurement variable at every point, and I have also the coefficient, the POD coefficient at every point. So then I go back, so I have this A, I have this S, and then I solve a least squares problem to extract the matrices that must multiply A, E, and S so as to give me as close approximation as possible for the training data set. So that's what I say here. I produce the data from the DNA simulation, and then I extract the matrices using system identification. And the method that I'm using here is the N4SID method, which is on MATLAB, which is, we use the MATLAB implementation. And then I test the model on a new set of data. When I say a new set of data, a new set of inputs, new measurements at one particular point, and that will give me the coefficients from which I can compute the full flow field. So this is what I have done. So how does this work now for my problem? So here I have on the left the contours of TKE from the DNS, and you can see here I have put a black dot at point 1. This is the point where I have the maximum TKE. Okay, and at this point I record the velocities UV and W. And on the right, you see this power spectrum, and you can see the peak at 1.5 FE. So you can see here that I have at this point a very complicated signal. Okay, the flow at this point is transitional. I have a random complicated signal. So I feed this signal together with my A coefficients, in particular A1 and A2, because I'm interested in the first two modes. I do the calculation of my matrices. By the way, this calculation takes a few seconds, 10 seconds, 15 seconds is very, very, very fast. And I get the model. And then what I do is, so I show you here the matching with the training data set, but what I want to do is focus on the validation data set. So I have extracted the matrices, and then I use the measurements at this point, okay, the measurement at this point at the following 40 rotations. So from 0 to 40, these are the measurements of that point on the validation data set. So that has not been seen by the algorithm. So the matrices that I have computed do not know these measurements. And then I compare with the and then I compare with the DNS. So you can see good matching. So certainly I can match very well the frequency, and this is not a trivial thing, okay? What I am giving to my system is this random signal that contains a very wide range of frequencies, but the algorithm, the model that I have computed, has extracted the useful information. So he has extracted the true frequency, and not only it has produced the true frequency, but in most of the cases, in most of the amplitudes, are also well predicted for coefficients A1 and A2. So the system has learned the physics. If I now put together the contour plots of the TKE, the turbulent kinetic energy of modes 1 and 2, on the left, I have the values from DNS. On the right, I have the estimated energy from modes 1 and 2, and you can see that is almost indistinguishable. Okay, so the model has learned the physics, and it has done a very good job at extracting modes, the temporal features of modes 1 and 2. What's happening now with instantaneous flow field? So on the left, I show you contour plots of the true velocity magnitude. So these are results from DNS, 20 rotations into the validation dataset. So, okay, I have a validation dataset which is 40 rotations, and this is an instantaneous snapshot at 20 rotations. At the 20th rotation. And then this is the snapshot, and this is what I get from the estimation at that time instant, again, using a single point of measurement can give me this information for the 3D flow field, this instantaneous information for this flow field, okay, using just a single experimental point. If I want to do now to modes 3 and 4, it turns out that if I use just one sensor location, the results are not so good, they're not so robust. I have to use 6 sensors which are located 60 degrees peripherally at all the peaks from the structures that are produced behind the blade. And you can see here how I compare the true values with blue and the estimated values with red. Okay, so now I have modes that I have smaller spatial structure, but so still I manage to predict well the frequency. In most of the cases, I can predict well the amplitude, but also there are some situations here where I miss it. As I increase the mode number, the estimation becomes more difficult because the spatial extent of this mode becomes shorter. So 1 point or 6 points cannot capture these smaller scale structures. So as I increase the model order, my accuracy becomes lower. Now, all of this now is from Reynolds number 600, okay? So I trained the model at 600 and I computed and I tested it at also mode 600. But really, what the powerful feature of this idea is if we can extend this to other Reynolds numbers which are not known, for which we haven't trained the model on. So what I have done here is the following. We have done simulations at 500 and 700. All right. I have kept the matrices that I have obtained from 600. So for 500 and 700, the only information that I give to my model is the actual measurements at these two Reynolds numbers, nothing else. All the training has been done at the previous, at the standard, at the design range. And then you can see the matching, okay? Even for 500 and 750, the matching is pretty good, okay? Even though we have done the training at 600. Now, this is telling me that, yes, there is, so it is robust to changes with respect to Reynolds number. And of course, I would expect that if I'm getting further and further away from the design, then of course I'm expecting intuitively that the accuracy will drop. Okay, this is nothing. So if I just use just one training point, this is what I expect to do. But of course, we can do more training. We can do more training. We can train at more points. So then we can cover more accurately a bigger strength, a bigger Reynolds number range, and then we can interpolate in between and find the reconstruction at any Reynolds number within the range over which we have trained. Now, all of this now that I have shown to you is results for which I have got it's somehow idealized in the sense that I have selected this point, I measured the three components, and I did the reconstruction. Now, what we wanted to do is to see, okay, what is it? Is there anything that we can do to make this less intrusive? So what we have done here is the following. We said, okay, we are not going to measure velocities, but let's measure pressure. So what you see on the left is the time average pressure on the impeller blade. So you can see that the time average pressure is from this side of the blade. So that is telling you that the blade is rotating in the counterclockwise direction. And here on the right, I have contour plot of pressure RMS. So the place, the location within the blade where I can calculate the root mean square of the pressure. So this is the contours of RMS of pressure. And you can see here with the green dot, the location for which I have the maximum RMS. And it is at this point that I put my sensor point. Okay, and then you can see I have here maximum RMS, but I have this point also here, which is close to the wall. And that makes sense because as the structures are radially propagating outwards, they impinge on the wall at this point and they create fluctuations there. Okay, but what I'm going to show you, results I'm going to show you are from points that are taken only at the blade. So this is the signal. Okay, this is the pressure signal at the location of the maximum. So you can see a very chaotic signal. Okay, and of course, do the spectrum, you can get again the frequency at 1.5 FM. So I feed now this signal into my. So I retrain my model and I feed this chaotic signal to my estimator. And then I'm going to show you here what happens. I'm going to focus only on the, no, here I have validation set for 1 pressure sensor and 6 pressure sensors. All right. So again, red lines are the estimated, blue lines are the true values from DNS. And you can see that even with 1 pressure sensor, it takes some time from my estimation to get to the DNS because for the estimation, I start from 0. Okay, I don't know what to start with. So I start from 0 value at A1 and A2. And you can see it takes about 40 rotations to get to the correct amplitude of the true data, of the true values. If I have 6 sensors, then very quickly, very quickly, I get to the correct values. And you can see that I can capture very well the amplitude, the frequency, and of course the amplitude, small deviations of the amplitude at various time instants. So it works therefore well with velocity data and pressure data. Now, all of this was for low Reynolds number, okay, 600. Does this idea work for higher Reynolds number? So I'm going to show you now results from LES simulations at Reynolds number 30,000. Again, this is unbuffled flow, unbuffled tank. So it's the same tank as you saw earlier, but the Reynolds number is now 30,000. And on the left, you see a contour plot of the mean magnitude of the velocity at a vertical plane that is bisecting two blades. Okay, so you can see that very close to the axis, we have very low velocities, and then this blue region here corresponds to solid body rotation. So the velocity starts from 0 here, radial velocity, and then grows. And then you can see also that we have a recirculation zone forming above and below the impeller. We have done comparison with experimental data and other DNS simulations, other LES simulations. So on the right, you see the trailing vortex path. So our work is with the solid lines, and the symbols, our works are from experiments and LES simulations. So we can capture very well the trailing vortex path with our LES simulations. Now, we did again the calculation, we computed the ROMs, we computed the coefficients, and what you see here are the time signals of the coefficients for 6 modes. Okay, so you can see here now mode 1 and mode 2, the signal, these modes are again paired. They have smaller energy content, if I remember correctly, is 5% with respect to the fluctuating energy. And then you can see now that they have a beating behavior. Now, this is very interesting fluid dynamical, something very interesting from the fluid dynamics perspective is taking place here. We have not looked at that, but it will be very interesting to look where this kind of beating behavior is coming from. So now we again trained our model. So again, we used data for a single sensor. It was located at the maximum amplitude of POD mode 1. And on the right, I'll show you, so this is the training data set, but it's the validation data set that it is interesting, because now we have a high Reynolds number. So now we have a turbulent flow, all right? So the blue results are the DNS. The red results are from my estimation using a single sensor at one point. And you can see it starts from 0 because I don't have anything to start with. So I start from 0, and quickly within seven revolutions, it captures the correct amplitude and continues to follow it. Okay, there are some locations for which I have some discrepancies, but let us not forget that it's just a single point on a three-dimensional turbulent flow field. Now, if we look at the instantaneous flow, okay, so this is again 20 rotations into the validation data set. So on the left, you see the instantaneous contours of the instantaneous velocity magnitude, which I got with my LES. So you can see structures that have a large scale, a large variation of scale. So you can see large structures close to the impeller, and you can see very smaller structures on the rest of the tank. On the right, you see the results that I get if I superimpose the mean and modes 1 and 2. So what you can see is that this plot on the right has captured the important features, the large-scale features of the plot on the left, but of course it has missed the small-scale fluctuations, okay? And it's obvious because if we're using just one point, we cannot capture the small-scale fluctuations. Small-scale fluctuations by definition have a small footprint, so we cannot capture them. But nevertheless, it's quite impressive that even with a single point, we can get this kind of three-dimensional unsteady flow that captures, which is really a smoothed out version of the LES, of the true results, the LES result. Now, of course, okay, all good, it works for a high Reynolds number, but again, the training was done at the training and validation was done at a single Reynolds number, in our case 30,000. Now, what happens if I look at off-design conditions? Because this is what we are really interested in. This is where the real predictive power comes. All right, we do the training at one operating conditions, and then we use the model to do optimization in other operating conditions. And that is really very powerful because it allows us to do very small training, to do the training at one point, but then allows us to do optimization in other conditions. So what you can see here on the middle and on the right are the results of A1 and A2. So these are the two modes. So temporal variation of A1 and A2 for two data sets, 20 and 40,000. And you can see that again, in these cases, the only information that I give is the value of the velocity at six sensor points, okay? 6 sensor points, and you can see that I can get very well the fluctuation frequency and also the fluctuation amplitude for off-design conditions. So that opens now the way to do some real-time, and this is all real-time, okay? Whenever I get the measurement in real time at the same time instant, I can compute A1 and A2. So I can do now real-time control. So this is where would be the next step. So, okay, so this is where we are at the moment. So I showed you how we can bring together experiments and simulation. So in this case, what I have done, it's all computational work. So the measurements that were coming were from DNS simulations, but this framework is designed to apply to experiments. So one can do all the analysis theoretically, computationally, and then merge with true experimental measurement. And then, of course, see the study accuracy, etc. Many questions remain. What is the optimal sensor placement? Okay, here we have used an intuitive method. We have looked at the location of maximum TKE, and this is where we put the sensor. If we put many sensors, is this always the best place? It makes intuitive sense. This is something we need to look at. Real-time estimation so here I have used measurements for velocity and pressure, but it may be possible to measure easier other variables like temperature or species concentration. So this is work that we have also carried out for different problems, and we can show that indeed it is possible using scalar measurements to reconstruct velocities, okay, and pressure field, etc. Now, as I said, now we have a real-time 3D evolution of the flow, and the next step would be, okay, how can I use this for mixing optimization and control? Now, for example, if I know the location, the spatial location of the vortex, can I now devise a method for which I can do, let's say, instantaneous feeding of a material where exactly the vortex, at exactly the same instance when the vortex is passing around my indector? Okay, these are the kind of problems that we can, this tool allows us to do. We can look also at two-phase flows, reacting flows. The bullet point here refers to parameterized ROMs in which we do the training not only at one Reynolds number I did here, showed you here, but we'll do it at different Reynolds numbers. So for example, if we have an operating range of, I don't know, from 1,000 to 2,000, then do training at 1,000, I don't know, 1,500 or 2,000. So 3 points, and then do interpolation between these for any Reynolds number within this range. So in that case, we cover a broader range, and we expect to have better approximation out of design conditions. Parameter estimation. This is also something that we can do. I will not go through. I will not say more here. If you are interested in the work on this work, we have a series of papers. You can have a look at these papers, or if you are interested, you can email me or ask me any questions that you want. So I'm done. I have finished. I'm now happy to take questions.
Great. Thank you so much, George. Very interesting and lovely to have another perspective on mixing and different ideas. I think in chemical engineering, we're always thinking about how to take the measurement, and you've brought it from a totally numerical point of view, and it makes us think differently, and I really like that because we can try and do different things.
Exactly.
Now we do have a question from Alain Linet. Alain says, "Thank you, George, for your impressive work. I have two questions. The first one is there any method or advice for fixing the number and the position of the sensors needed to reproduce the time evolution of the coefficients? And the second question is, have you implemented this technique during experimental measurements in a stirred tank? If so, with which sensors?"
So the first question. So the answer is yes. There is a way, a mathematical way to find nearly optimal, not exactly optimal, nearly optimal sensor locations. So in reality, this is an NP-hard problem in the sense that if I have, let's say, a pool of 10 sensors and I want to find the two best sensors, then I have to do simulations with all the different permutations, 2 out of 10. But there are ways where we can do have a mathematical tool based on QR decomposition of an appropriate matrix to approximately find where the best locations are. So we have done work on this, and would be happy to talk to Alain on this later. So this can be done. The second question is, so we have not implemented this technique on experimental work. So we have continued this work. So this work has started with stirred vessels. Now we have moved to flows around buildings for which we can have measurements, real measurements. I'm working with experimentalists on this, but we haven't yet produced anything. So this work at the moment is, so there is experimental interest from the experimentalists in our department to work on this. So we are setting up the problem now, but at the moment I don't have something to report on. But the idea is that we can do that and to use experimental data. That would be the idea.
Mm-hmm. Can I just read, because I had a question also on the sensors in that sense, because ideally in an experimental measurement, we'd be, putting one or several sensors in a stirred tank. And in your simulations, you have very, very small time steps. So you have an acquisition frequency that's very, very high. And practically, we usually don't have such a high acquisition frequency. So what impact would that have on the prediction of the flow field, for example?
So there is no problem. So in the result that I showed you, because it's all coming from the DNS, the same time so you've got concurrently the DNS and the measurements, all right? But it doesn't have to be at the same time instant. So what you could do is to say, okay, my simulation has a time step, let's say, of 0.1, and I have a measurement every 1 second. It's absolutely no problem. The algorithm can work, so it will do whatever it will do from 0 to 0.9. At 1, you will get the measurement. It will correct, the filter will correct what it will get based on your measurement, and then it will continue. No problem. It is straightforward.
Okay. All right. Thank you. Right. So we have a second question from Salah Hosseini from Toulouse. Thank you very much for this interesting talk. My question is about the machine learning method. If I understand correctly, the learning method is supervised. Therefore, for this reason, we cannot expect to have accurate estimates for unseen data, especially for external rather than validation data, and of course for different geometries. So in your point of view, can reinforcement learning help us train the model much smarter, especially for different stirred tanks with different geometries?
So what I have shown to you is linear estimation. Okay, so if you have a linear problem and you have training data, then the optimization problem to extract the matrices is quadratic. So you minimize a quadratic function, okay? And that you can solve using least squares. So that gives you a unique solution, okay? So what the Said mentions is machine learning. Machine learning, you can interpret what I have done as machine learning, but with a linear model, in which case it's a special case for which I can get exact unique solutions. Okay, very, very, very quickly, within a few seconds or less than a minute, I can get these solutions. Now, I haven't interpreted this, I have not presented this in terms of machine learning because I don't want to confuse things. Okay, so I said it's linear system identification. Now, so we don't have any problem, as I say, to unseen data. So we have used unseen data on the training, on the validation data set, so it does work. Now, I cannot answer the reinforcement learning question because I know that there is a very large aspect of machine learning which is called reinforcement learning, but I cannot really answer this question because I don't have experience on that.
Thank you. We have another question from Yu Jiang. Thank you for the impressive talk. I have the following question. It seems that the ROMs are not parameterized ROMs. Yeah. Then how is the trained ROM derived from one single Reynolds to be able to predict off-design Reynolds cases?
So,
what is the principle behind the mechanism?
So the idea is that once you get the matrices for one Reynolds number, you assume that these matrices will not change if you move to a different Reynolds number. So then you have the matrices obtained for one Reynolds number. You have, on the right-hand side, you need only the measurements for that different Reynolds number. So the coefficients, the matrices remain the same. So then you use the real measurement from the other Reynolds number to extract the time series, the time coefficients. Of course, because you don't do any training on the new Reynolds number, so the matrices remain the same, but also the modes remain the same. So if you want to do reconstruction for the new Reynolds number, you have to compute, you have now the coefficients, but you have to multiply them by the modes that you calculated for Reynolds for the original reference case, right? Because you don't have anything else. Now, if you want to do it in a more accurate way, then you have to do the training. Let's say, as I said in the example, if you have a Reynolds range from 1 to 2000, you can do it at 1000, 1500, and 2000. So then you have three data points for which you train, and then you can then have measurement at an intermediate point, let's say 1200, but then because you have trained in three different locations, you can interpolate, and there are different ways to do that. We have also done that. And then you can get something more robust and more accurate. The other thing that I want to say is that because these are linear models, the eigenvalues that we get for the matrices are stable. Okay, so then we don't have the problems that sometimes appear when you do these kind of things for machine learning, where you get models for which, if you integrate for a long time, the results exponentially diverge. We have linearly stable system, which is very, very important if you want to do real time in reconstruction without the result exploding exponentially.
Mm-hmm. Okay, so I had a question that relates to this.
Yeah.
So does that mean? I mean, I'm just surprised that, and perhaps it wouldn't work. Does it still work if you change flow regimes? Because the flow regime, the mixing mechanism in laminar flow is very different from the mixing mechanism in turbulent. So how does it work?
So in that case, so if you have a Reynolds number regime for which you have variations in the physics of the flow, so the solution would be to do the training at different Reynolds number.
Okay.
But if you are, for example, in the Reynolds number regime, for which you have self-similarity, then I would expect that because of the self-similarity, you don't need that many training.
Yeah.
But this needs to be tested. It would be very, very nice if we say, okay, we have self-similarity. How can we exploit now the self-similarity to do one training and be able to use it in a range of Reynolds number, provided that the fluid, the mechanics is self-similar? That would be a very interesting thing to do.
Okay, so that means that in a stirred tank with baffles in the transitional flow regime, we might not be able to find a way to do it because we don't know if it's the flow is really self-similar in that way.
Yes,
in
so
that
in
area.
that case, the only thing that can really give you good results is to do with lots of different data, a lot of different Reynolds numbers that cover the full range of transitional range, and then you are in a more secure ground. Otherwise, but that's all very interesting questions.
Yes. Okay. Thank you. So we have one last question, I think, from Tobias Shikaraski. Very nice talk and results. How much do the fixed matrix coefficients depend on the geometrical arrangement of your stirred tank? For example, if I place a feeding pipe where the flow interacts with the trailing vortices, do I need to resolve the full linear system again?
A very good question. So I think this will depend on how much this feeding pipe will affect your flow. So if the scale, if the feeding pipe is much smaller compared to the vortices, then I don't foresee, then I hazard the guess that it will work well. If, on the other hand, your feeding pipe is much larger, is on the same order of magnitude, quite large, on the same order of magnitude as your vortices, then it may affect the vortices themselves. Okay, but then, so then what you can do, I mean, the only thing you can do then is to take into account the presence of the feeding pipe, and when you do the LES, include the geometry of the feeding pipe within your POD, within your simulations. Now, so I do not have, so if that's my qualitative answer to this question, depends on how big is your feeding pipe with respect to the structures that you are interested in.
Sounds sensible. Great. Thank you. Thank you so much, George. That's the end of the questions. So I'd just like to thank all the participants for joining us today. I mean, we had a great turnout, and I hope that it's been useful to everybody, whether you've used reduced order modeling before, or if you just wanted to try and understand a bit more what it was about. I'm sure both of those presentations will enable you to show you how it can be used and give you a little bit more information on what it is. Yes, I'd just like to thank both Kit and George for taking the time, preparing the presentations, and being with us today.
No problem. Thank you. Thank you very much.
Great.
Thank you.
And thank you again to Martin for having organized the logistics and organized all the series, the Spotlight Talk series. So you can enjoy other Spotlight Talks over the next 10 days. Just look on the EFCE website if you want to register for other ones that you are interested in. Thank you very much, everybody.
Thank you. Bye.